Assalamualaikum warahmatullah. So, welcome to our first topic, that is Subchapter 1.1, Laminar Flow Through Circular Pipes Under Steady and Uniform Conditions. So, for this subchapter, we are going to apply the hydraulics knowledge in civil engineering field, and the program outcome for this subchapter is to apply the knowledge of mathematics, natural science, engineering fundamentals, and engineering specialization toward practical procedures and practice. So the learning outcome for this subchapter is, at the end of this lesson, students should be able to apply the Hagen-Poiseuille equation on laminar flow in bounded system, and to apply the Darcy-Weisbach equation on laminar and turbulent flow in bounded system, and third, to determine the flow friction factor F using the mooc chart, and also the last one, to determine the head loss in pipe due to friction, separation, and also pipe fittings. So let's look to the first content. This is the introduction of this subchapter. So it deals with the analysis of pipe flow running under steady and uniform condition. So the pipes are analyzed for both flow, laminar, and turbulent. So the head loss due to friction will result from the shear stress derived by both laminar and turbulent flow. So the head loss also result in flow separation. So for the uniform flow, so when we're talking about the uniform flow, the fluid flow in which all the conditions at any one point are constant with respect to space. This means that when the flow is traveled along the pipe from point A to point B, the speed, the velocity is constant throughout this pipe. So that is considered as uniform flow. How about steady flow? So when the fluid flow in which all the conditions at any one point are constant with respect to time. Meaning that when the flow is traveled throughout this pipe from time 1 until time, let's say 10 minutes, so it traveled along this pipe within 10 minutes at a constant velocity or flow rate. And now we look into the laminar flow in circular pipes under steady and uniform condition that can be analyzed theoretically by applying the momentum equation. So the relationship between the shear stress and the velocity gradient is utilized to obtain the velocity distribution within the cross-section. So there is also a no-slip condition. It is used for a given fluid where the velocity of the fluid in contact with solid boundary is equal to the velocity at the solid boundary. So the stationary pipe case is when the velocity will equal to 0, meaning the flow is not moving. The water in the pipe is not moving, so the velocity is equal to 0, and the velocity of the fluid at the location where it is in contact also equal to 0. So let's look at this figure. So this is the cross section of the circular pipe. So the R is the radius measured from the center of the pipe, okay, until the boundary of the pipe, the border of the pipe. So this is the radius, R, capital letter R. And now we are talking about the molecules, the velocity of molecules from the center to one location, and we label as R, small letter R. Okay, so there are also the difference of the length or distance from the border of the pipe to the location of the molecules that going to be measured. Okay, so that is the delta R. Alright, so when we look from the side view of the flow, so we can see from this figure the maximum velocity is happen at the center of the pipe. Alright, and when it comes near to the boundary of the pipes, the velocity will reduce because the shear due to the pipe boundaries. Alright, so therefore it will cause the reduction of the velocity. So this is the figure, alright, from the side view of the pipe, alright, from point A to point B. And then we can see that is the radius of the pipe, R, capital letter R. And then this is the molecule that being measured, the velocity that being measured, okay, labeled as small letter R. And then we also have the weight of the velocity and also the elevation of the pipe from the datum, and also the angle, the tilting angle of the pipe. Okay, so the velocity is moved from the point A, okay, upstream to the point B, downstream. So the arrow is to the downstream, downward. Alright. So it also have the density, okay, velocity distribution in pipes due to laminar flow is caused by the density that labeled as rho, and also the momentum equation applied to the annular element and summing the force and equating them to the rate of change of momentum. So this is the force in the direction of motion due to pressure, and then we have the shear stress and also the weight of the molecule. So we can see the weight acting downward, and then we have also the shear stress that opposite direction to the movement of the flow. Alright, we can see the arrow is going opposite direction, right? And then we also have the pressure. The pressure will force the molecules to flow throughout the pipe. Alright, so we will look into the pressure in the next video. Thank you.